Hi everybody and welcome to the 15th lecture of Digital Communication course. In today's lecture we will be talking about M-array phase shift keying and M-array quadrature amplitude modulation schemes. In the previous lectures we talked about binary phase shift keying and the quadrature phase shift keying. Up until now these are the key modulation schemes that we discussed so far. And we said how many bits we can transmit with binary phase shift keying. Each signal, each symbol carries only one bit. Whereas with quadrature phase shift keying, each symbol carries 2 bits. So basically we said that we can double the data rate and have the same bit error rate if we use QPSK modulation technique, which is very significant thing to achieve. Why do we need to increase the data rate? Why do we need to send more bits per symbol? Because there are applications that are data rate hungry, like video, like real-time streaming, like gaming, like virtual reality application, augmented reality, mixed reality. All these applications require extreme high data rate. Yes, with MPSK you can only send 1 bit per symbol. This is not efficient. This doesn't increase your data rate much. With QPSK we were able to introduce schemes, we were able to achieve 2 bits per symbol, 2 bits per symbol. Now we need to come up with new modulation schemes if we can that can provide even further enhancement in the data rate. That's why we talk about M-array signaling schemes in this lecture. And the key motivation behind this is the availability of many applications in real life that require high data rates, high data rate speeds, with the knowledge that we always have limited bandwidth. The bandwidth is always limited. Your goal here is within a limited bandwidth, you want to squeeze as many data bits as you can so that you increase the speed of your internet. That's why it's desired to transmit more than 1 bit using a single carrier. Yes, more than 1 bit using a single carrier. This is what's M-array signaling schemes if you want to define it. Sending more than 1 bit using single waveform, single carrier. Modulation schemes that are designed in this manner, we call them M-array signaling schemes. So M-array is basically having different levels of certain modulation scheme. When you have many levels, when you have large number of levels, you increase the number of data bits you can encode to each level. For example, in this case, all the basic modulation schemes that I taught you before, like ASK, FSK, PSK, you just can add M in front of them, just as a prefix, and then you have M-array, means M different levels of this modulation scheme. For example, if ASK has 2 levels, ASK when 0 comes, you don't send anything. When 1 comes, you send the signal with amplitude. When you have M-array of ASK, you have many amplitude levels. This is 1 level, this is the second, this is the third, this is the fourth, this is the... As M increases, you have different amplitude levels. What about FSK? The basic concept, the basic scheme of FSK has only 2 frequencies, but with M-array FSK, you can have M number of frequencies. What about phase shift keying? It's the same. Instead of having 2 different phases, you have M number different phases. So how to design this modulation scheme? How to transmit your data using this scheme, and how to receive it and decode it? And what would be the bit error rate performance? What would be the spectral efficiency performance? How do you choose between these different modulation schemes based on the application you are trying to serve. So after this lecture, and by studying all these different schemes, you will be able to answer all of these questions. And you, not only this, you will be able to think beyond that and come up with maybe different new kind of techniques that can improve your system performance further. So it's possible to generate M-array signals by combining more than one modulation scheme. The other thing that you need to know about is not only you can have different M values of each basic modulation scheme, but also you can mix between them. You say, why don't I change the phase and amplitude together? If I change the phase and amplitude, I get more number of combinations. Yes? More number of possibilities. Yes? When you have these extra possibilities, then you increase the data rate. Because, for example, if you can have 8 different values with amplitude and another 8 different values with phase, then if you combine both together, how many different values you will get? 8 multiplied by 8, 64. If you combine them, you get 64 different values. So with 8, you transmit only 3 bits, because 2 to power how much equal 8? 2 to power x equal 8. What's x? 3. But when you have 64 values, 2 to power how much equal 64? 6. So instead of transmitting 3 bits per level, here you are transmitting 6 bits per level. Why are you able to achieve that? Because you combined 2 different properties of your carrier, the phase and the amplitude together. What do we call these schemes? We call them hybrid. Give me an example of hybrid modulation scheme. Amplitude phase keying. You change the amplitude and phase simultaneously. Also, MQAM, another modulation scheme that's actually hybrid and uses the amplitude and phase simultaneously in the 2D constellation diagram. So, with that being understood, now we move to study M-array phase shift keying in details. The signal in time domain, the signal in the frequency domain, the bit error rate, and the spectral efficiency, and how increasing the number of levels can improve the data rate and how it impacts your bit error rate performance. You need to know this. So in this case, theta I, in the case of M-array phase shift keying, theta I is dependent on the number of values. For example, if you have binary MPSK, how many different phase shifts? How many different phases you have? Only 2. One at 0 and one at pi. If you have 4 QPSK, how many different phases you have? 4. 1, 0, pi over 2, pi, and this 2 pi over 3. 270 degree, 0, 90 degree, and 180 degree. Yes, these are the different phases. Now, if I tell you I'm gonna use not 8 different phases, but not 4 different phases, but 8 of them. So what will you do? How do you put the points in the constellation diagram? You put one here. The distance between all the points should be the same, uniform. You put one here, another one here, another one here, and another one here. Yes, how many points now you have? You have 8. What's the phase between any 2 points? Can you find? From math, how do you find it? You divide this, the angle of the circle, how much? 2 pi. Yes. complete circle, 2 pi over the number of points, which are m, 2 pi over m. If you have m equal 8, 2 pi over 8, how much? 45 pi over 4. So this is the angle. I can ask you these questions. It's possible that I can change the value of m and ask you what would be the phase difference between any 2 points. It's logical. By logic, by math, you can find it. Now, this is 2, this is pi, this is m. Then the phase at any instant can be function of I. For example, if you start from 0, then I must be 1. 1 minus 1, 0. 0 multiplied by anything, 0. So that the first theta 1 is equal to 0. You put the point here. I can tell you, draw the constellation diagram assuming that theta 1 starts from 0 or starts from 45. Yes? So when I is equal to 1, theta I is 0. When I is equal to 2, theta I 45. And so on and so forth. You can draw the constellation. Now what do you conclude from here? As m increases, the phase, the angle between the points with respect to the origin decreases. Yes? Which means that the points get closer to each other. If the points, which represents the message that you are transmitting, get closer to each other, what happens at the receiver? Becomes more difficult for the receiver to distinguish between them if they are impacted or affected by noise. Is that true? So there is kind of a trade-off. When you increase the number of the points in the constellation diagram, you increase the number of bits you can transmit with each level, with each symbol, but the points get closer to each other, which makes it difficult for the receiver to detect, and it becomes more probable to have errors in the detection process. So your data rate will increase. This assume this is the power signal to noise ratio here. This is the curve, and this is data rate. Your rate will increase when you increase m, and you increase the signal to noise ratio. But unfortunately, the bit error rate will become worse. Like instead of having this bit error rate, you get this, which is not that good. We will explain and understand this in more depth as we proceed in the lecture. Now, one might ask, can you write the mathematical formula that represents M-array phase shift keying in general? So I say phase shift keying means I only change the phase of the carrier, and assume I'm using cosine. Then I write cosine 2 pi fct, where fc is the carrier frequency and t is time, your signal function of time, plus you put the phase here that you found here, just here instead of the original phase. Before we didn't have this term. Now since it's changing the phase continuously, so we put the value here. And the amplitude, this is the amplitude, it's always there. Now you must just give me your attention and see with me that E here is not the energy per bit, it's the energy per symbol. So when you have 8 phase shift keying, M is equal 8. What's the energy here? The energy of the symbol equal to the energy of 3 bits, because each symbol in 8 phase shift keying carries 3 bits. And T here also is the duration of the symbol, not the bit. Yes? So the duration of one symbol is equal to the duration of 3 bits. Clear? Are we clear about this? Don't confuse this. You must be aware that this is not per bit, per symbol. And based on the M value, you decide how many bits each symbol represents. Clear? and I can take the values from 1 to m. So this is the mathematical formula, this is the model of your transmitted signal that you modulated with M-array phase shift keying. Are we fine now? Is everything okay? Now based on M, you can be asked to draw the constellation diagram. Or sometimes we call it signal space diagram for M, for example 16, for M 64. In this case I'm drawing it for 8. When you draw it for 8, you put this is M1, this is M2, based on the angles, of course. You will find the angles exactly. M3, M4, M5, M6, M7, M8. You have 8 different messages or symbol points. Yes? Now, you need to determine the boundaries between these points. At which point, at which border, I will start deciding whether the symbol is in this region or in that region. Suppose that you transmitted your signal, yes, and your signal, instead of receiving exactly here due to noise, you received it here. You transmitted M3 at the transmitter, but unfortunately, due to having noise in the channel, your symbol at the constellation diagram, you received it here. So the receiver has to decide, is this M3 or M2? Because it's in between M3 and M2. For the receiver to decide that, he has to consider a boundary. Yes? And that's why you draw these boundaries. This is the boundary, this is the boundary, these are boundaries to determine and decide. If the symbol is to the right side of the boundary, of this boundary, and below the phase of this boundary, then it's M3. You decide it's M3. If it crosses this and comes here, it becomes M2. And you record, this is one error, one symbol error. This is how the receiver figures the error. Now we have constellation points, we have boundaries. We can now find the probability of error. Yes? What was the probability of error for binary phase shift keying? It was ERFC. Yes, it was ERFC complementary error function of square root of EB over N naught. Yes? Now, what would be the bit error rate multiplied by half? What would be the bit error rate of M-array phase shift keying? Not 2 phase shift keying like binary phase shift, M values. What would be? To do that, you need to determine the distance between the points in the constellation diagram. So where is the distance here between the points? Everybody can see with me? Here, this is the first message, yes? And this is the second message, yes? This, everybody can see with me here, the messages. M1 and M2. You need to find, I can ask you, find the distance between these 2 points. Direct distance, this. You tell me, okay, I know the amplitude of the first message. All of these messages, they have the same amplitude, square root of E over T. Yes, this is the amplitude, isn't it? This is the amplitude. Here, after you normalize and everything, it becomes square root of E. And I know this angle, yes? From where you know this angle? Because I know the angle between 2 adjacent phases. How do you know it? 2 pi over n. True? Now I know angle, and I know that when I take this line perpendicular to this, I get here 90-degree angle. So it becomes like Pythagoras. Now your goal to find this. Can you find this? You tell me yes, it's easy. If from the sine law, Yeah, you know the sine law? Laws of sines and laws of cosines. You don't remember it from math. It says that if you have any triangle, then sine this angle A over this segment A is equal to sine this angle B over this segment B, which is equal to sine C over the segment C, the length of the segment C. You remember it, I think, from one of the courses. This is, we call this law of sines and this law of cosines. And this is what cosine is, and this is what sine is. The opposite over hyperbolic or adjacent over hyperbolic. Now, having this knowledge in math, you can come here and find the distance, yes? You tell me this is sine I have. Now, based on this, let's take this here. So that everybody can see with us. What I have this. This is 90, and this angle is pi over m. Yes? Why pi over m? Why not 2 pi over m? Because I'm halving it. Here pi over m and here pi over m. When you sum them, 2 pi over m. Because I'm taking only one triangle. The other one is reciprocal to it. And you have here 90, and I know this, the length of this from here to here, square root of e. So from law of sines, you have what? You have sine pi over m, yes, over this distance d, which is actually half the distance between 2 points. This is the whole distance from m1 to m2 is d. So this distance, how much? Half d. Yes? Which is equal to sine 90. Sine 90, how much? 1 over square root of e. Yes? Then what's d? D is equal to 2 square root of e sine pi over m. This, we call it the distance between 2 points in the constellation diagram. We care about it because it affects the bit error rate performance, the probability error performance. Clear? Now you can find the phase, you can find the distance, you can find now what? The bit error rate. This is distance from message 1 to message 2 is the same as distance from message 1 to message 8. And it's equal to 2 square root of e sine pi over 4. Now, here I showed you how to derive it. I can ask you about the derivation. Although it's given directly here, but I explained to you how to find it. Yes? Not difficult. Now, all what you need to go to the error rate formula and substitute, consider the distance value, the Euclidean distance. This we call it the distance between two adjacent symbols or two adjacent message points in the constellation diagram. We call this Euclidean distance. And the error probability becomes square root of e over n naught multiplied by sine pi over m. For m values greater than or equal 4. Now, we found the error. You can go to MATLAB and draw the error rate. Probability of simple errors. This the blue curve here represents MPSK. This represents 8 array phase shift keying, the green one, and the red one represents 16 phase shift keying. Okay, this is 16, this is 8, this is 4. Now I can tell you which one of those has the best bit error rate performance. Which one of those has the best bit error rate performance? From the figure, the best bit error rate, the best probability of simple error. I want the error to be as minimal as possible, as low as possible. Among these, which one has the least error? The blue one. So you can say MPSK is better than 8 MPSK, better than 16 in terms of error, because it reduces the error. Which one has the worst bit error rate? The red one. Because see here at this EB over N naught is the signal to noise ratio actually, and this is the probability of error. 10 to minus 20. What does it mean? 1 over 10 to 20. In each 10 to power 20 bits you are transmitting, you get only one error. So as you go down and you go to the left towards y-axis, your performance becomes better. Now we know the formula of 8 array phase shift keying in time, but what if we want to draw the modulation scheme in the frequency? We know we want to see its characteristic in the frequency and how much bandwidth it occupies in the spectrum domain. To do that, we need to go to the Fourier Transform. You already have this, yes? Everybody know this is psi of t. Yes, this is the transmitted waveform in time. You take the Fourier transform of this, you go to the frequency domain and take the power of it, multiply by, take it to the power 2, you get the power spectrum, yes? The power spectrum, after you calculate and do the calculation and integration, you find it to be 2e sinc square TF. Now this is for symbol, E for symbol, T for symbol. If you want to substitute it in terms of energy of bit and time of bit, then what's E? E is equal to EB, yes, the energy of one bit multiplied by the number of bits per symbol, log 2 M. And here it is. This value is basically E. And T, what's T? T is equal to TP, the duration of one symbol equal to the duration of one bit multiplied by the number of bits per level, log 2 M. If M is 8, T is equal to 3 TP. So the power spectral density becomes this. If I tell you what's the power spectral density for the case when M equal 2, you just substitute here 2. Log 2 equal 1. 2 to power 1 is equal to, and the final answer becomes this. So this can be in a multiple choice question, for example. I change M and tell you which of the following formulas represents the power spectral density of 8 phase shift keying. I just changed the form. You need to know which one. Now, after drawing them in the spectrum domain, in the frequency domain, you can see that as M increases, it takes less bandwidth for the same data rate. Yes? As you can see here, why the bandwidth or the frequency reduces when you increase M? Anybody has any idea? Any smart student, clever, intelligent, sharp, who can answer this question? That I will ask it in the exam as well. Why do we have shorter bandwidth, small bandwidth, as we increase the modulation order M? I just mentioned it here. When you increase M, what happens to the duration T? As M increases, the symbol duration, what happens? Increases. As you increase M, T here increases, yes? If the duration increases, T, if from signal and system course, frequency characteristics, when you shrink your pulse in time, it increases in frequency, yes? When you increase it in time, it shrinks in frequency, yes? This is the reason. Now, this has the largest symbol duration because it's 3 TB. Since it's the largest duration in time, it has the lowest bandwidth in frequency. So we call it's spectrum efficient. It's a spectrally efficient modulation scheme. With less bandwidth, you can transmit the same data rate. Yes? And this is as you reduce M, the normalized frequency increases, and it's the biggest actually for the case when M is equal to 2. You understood this? Is it clear? Very important. Now, I can ask you, what's the bandwidth efficiency of this modulation scheme? In bandwidth efficiency, we care about null-to-null bandwidth. How to draw null-to-null? You extend this, make it reciprocal. Yes, and draw. You extend and draw. You extend and draw. Okay? You care about the duration from here to here. Yes? What's the bandwidth here of the main loop? The bandwidth from here to here. The bandwidth is equal. This one 1 over t, and this minus 1 over t. Yes? What's the distance between them? 2 over t. Yes? So the bandwidth, the main loop, null to null bandwidth is equal to 2 over t, which is equal to 2 over tb log 2m. Yes, because t is for symbol and tb for bit. And tb, you can take it from the denominator and put it in the numerator, and it becomes rb, bit rate. Then the final value is 2rb over log 2m, where b is the bandwidth of the transmitted data, and the bandwidth efficiency of M-array phase shift keying can be given as follows. Rho is equal to the data rate you are transmitting over the bandwidth. What's the data rate? RB. You put RB. What's the bandwidth? The bandwidth, we found it here. It's this value. You divide over it. The final result is half log 2m. Now I can ask, the bandwidth efficiency increases with m or decreases? Increases with m or decreases? The bandwidth efficiency increases with m. As you increase m, you can transmit more bits per symbol. Yes? That's why we are using M-array phase shift keying, to increase the spectral efficiency of your system. So this is basically M-array phase shift keying. The same you can apply it to M-array frequency shift keying, M-array amplitude shift keying. But what's more interesting is to make hybrid modulation schemes, exploit the amplitude and phase together to send more data bits. How to do that? we can achieve that by using a modulation scheme called M-array quadrature amplitude modulation. This QAM stands for Quadrature Amplitude Modulation. You change the amplitude and phase of the signal simultaneously. Both amplitude and phase of carrier change according to the transmitted symbol MI. What's SI of t, the transmitted symbol in time domain, that represents this modulation? It's square root of 2E0 over t multiplied by AI, this is the new thing, multiplied by cosine, minus the amplitude multiplied by BI. Now BI, by changing AI and BI, you change the amplitude and what? The phase. Yes? Is that true? EB is the energy of the signal with the lowest amplitude, and AI, BI are integers. So this is basically what you get. You get this transmitted waveform that uses two basis function, phi 1 and phi 2. Phi 1 is cosine and phi 2 is sine. These are the basis function in the constellation diagram. This is I in phase and this quadrature. This in phase phi and this quadrature phi 2. These two basis function, we use them in the construction of the modulation scheme called the QAM. Now, the resulting constellation can be square or rectangular, depends on the number of data bits you are transmitting per symbol. For example, if you are transmitting 4 bits per symbol, you have square or rectangle. 4 bits, you have 16 points. You can put them in a rectangle or square. But if you have 5 bits per symbol, which means M equal to 32, you cannot put them in a square diagram. You must consider rectangle. Square is exactly has the same. This is square, this is rectangle. This is we use it for odd number of bits per symbol, and here for even number of bits per symbol. So a question can be like this: 64 QAM modulation uses square constellation diagram, true or false? 64. Square or prime? Square, because number of bits 6, even. QAM square constellation having even number of bits per symbol denoted by 2n. M is equal to L multiplied by L, and L is equal to square root of M. For example, here, what's M? What's M? The number of points you have. How many? You have 16. What's L? L is the dimension in X or Y axis. Square root of M. Square root of 16 is equal to 4. And what are these values? This is AI and this is BI. The amplitudes of your cosine and sine, the amplitude of the basis function. This is the constellation diagram of 16 QAM. As you can see, is it square or rectangle or a triangle? Square. And here the constellation diagram of 4 levels of pulse amplitude modulation. What do you see here? You see QAM as if it is multiple layers of pulse amplitude modulation, yes? Multiple layers. This repeated 4 times. This very important feature that we can utilize while we are deriving the bit error rate performance of QAM modulation. Now, to calculate the probability of error for a QAM, we can consider the fact that 16 QAM is a combination of two 4-array pulse amplitude modulation, like I said here. Each point here is actually coming from two one-dimension 4-array pulse amplitude modulation. One vertical, one horizontal. Doesn't matter vertical or horizontal. At the end of the day, it gives the same. So for each system, 4-array pulse amplitude modulation, you can find the error probability. The error probability is basically 1 minus 1 over square root of m multiplied by the complementary error function of square root of E naught over N naught. This is only for one line, pulse amplitude modulation. You have also another line that can bring you error. Yes, this is for the horizontal, let's say. There is another one that's vertical. Also brings the same error because it has the same structure, but instead of being horizontal, it's now vertical. Yes? So, what's the total error? The error coming from the vertical multiplied by the error coming from the horizontal. So what's the probability of receiving your symbol correctly? It's the probability of receiving your symbol correctly from the vertical line multiplied by the probability of receiving your symbol correctly from the horizontal line. From the vertical line, it's 1 minus PE. And the horizontal line, also 1 minus PE, multiply them, becomes a square. Now, what's the probability of error? The probability of error is 1 minus probability of correct reception. Yes? You substitute probability of correct decision, its value here, and you end up getting this final value, which can be approximated to 2 PE prime, which is the error probability in QAM modulation schemes. Therefore, the error probability can be written in this form: 2 multiplied by 1 minus 1 over square root of m multiplied by the complementary error function square root of E naught over N naught. Now this E naught is not the average energy. Why it's not the average energy? Because we have different constellation points here with different amplitude values. The energy of each constellation point is not the same for all of them. Yes? Here they have different amplitude from the origin. The energy cannot be the same. So we cannot use the energy of the energy of lowest symbol or the energy of highest symbol. We need to average them. To average them, we use this formula. E average is equal to summation of all the constellation point, 2i minus 1 square, from I equal to 1 to L minus 2, multiplied by 2E naught, which is the lowest energy level, over L, and you get the E average, which after you simplify it, you find out that this E average is equal to 2 multiplied by M minus 1 multiplied by E naught over 3. Now this value, you can substitute it in this error formula and to get the final expression of the error probability in QAM modulation, which is this. This is the final error probability of QAM modulation. Now, what do you think, the error probability in QAM modulation worse or better than the error probability in M-array phase shift keying? This is a question you can ask. To do that, you just take this formula and draw it in using MATLAB, and take the formula of that, draw it for the same M value. After you do that, the result that you have to get in MATLAB is that bit error rate of QAM is lower than the bit error rate of phase for the same data rate. I can ask you why. Why is that? You tell me because in QAM I have 2 degrees of freedom. I am changing 2 things together. But in phase, I am limited to only one feature. So when I add more points, they get crowded in the phase domain. But in QAM, I have the amplitude domain. I can go to it. I can escape. In phase, you are limited to put your points on a circle. You cannot exploit the amplitude. But with quadrature, you can put them not only in phase, but also you can increase the radius of the circle, which means you increase the amplitude of your symbol. Since you have this freedom, you are flexible to move, then what do you get? You get larger distance between the points. Since there is larger distance between the points, your error gets reduced because the boundaries now, it's not so critical as the case of M-array phase shift keying. Now, having discussed M-array phase shift keying and M-array quadrature amplitude modulation, we can see one common feature in all of them. This feature can be summarized as follows. As you increase the number of modulation levels, M value, you can transmit more data bits per symbol, but the error gets worse. This observation applies to all the classical modulation schemes, whether M-array phase shift keying, M-array frequency shift keying, M-array amplitude shift keying. So the point is that, can we come up with a modulation scheme that can provide us improvement in both domain, in bit error rate and data rate simultaneously? Now, these are the schemes we studied and we found there is a trade-off. If you improve something, you lose something. For example, bit error rate is the best modulation scheme in terms of error, low error. But it's the worst in terms of data rate. While 64 QAM is for example, it can be better than the other modulation schemes that has lower modulation order, but its bit error rate is very bad. So it's a trade-off. How do you decide which modulation scheme you use? The application. If the application is video, what do you use? MPSK or 64 QAM? Video. 64, you need more data rate. But if the application is messaging, what's up? Message should be received correctly with no errors. You use MPSK. You don't care about the data rate. I don't care if it reaches now or after 1 minute, it's fine. But the most important thing that the message reaches correctly. That's why MPSK for messaging, for example. 64 for gaming, for video application, streaming, this and that. So I want you to think about this, the statement that's written in bold line. The challenge is to come up with a new modulation scheme that has no trade-offs between spectral efficiency and bit error rate. Is that ever possible? And if yes, then how to do it? This is a research question. It's not solved in the literature. No researcher was able to come up with a scheme that can solve this problem. It's open problem. If we can come up with a solution for it, it's gonna be groundbreaking. A modulation scheme that can increase the data rate, also reduces the bit error rate simultaneously. There is no trade-off, and does not necessarily needs to be complex. Now another question that came to my mind, which modulation scheme is more complex to detect, MPSK or 64 QAM? More difficult to detect the symbols. The receiver is more complex means. 64, why? Because it has more symbols. You need to decide, the for loop is 64 values. But for MPSK just 2. Which one is faster? 2. You compare it quickly. So this is basically what Quadrature amplitude modulation, M-array phase shift keying, the advantages and disadvantages, how to find the bit error rate, the spectral efficiency, the trade-offs between them, how to use them for different applications, and how to come up with different modulation schemes that can enhance the performance more and more. So with this, we finish our lecture and meet you in the next lecture, inshallah. Thank you.